So, starting with the overview of the interTwin project. As you can see, our project started in September 2022 and is going to finish in 2 months from now at the end of August. We had a budget of approximately 12 million euros, 11.7, and our consortium consists of 30 partners plus one affiliated entity and 2 associated partners, consisting of 10 resource providers for cloud, HTC and HPC resources, 11 technology providers for the horizontal capabilities, and 14 community representatives that were participating through our use cases and the digital twin applications, basically. The background, for those that are new to the topic. So a digital twin is a virtual representation of a physical object, a process, or a system. It is developed and sustained with information derived from one or multiple data sources. It can be sensors, models, it can be historical and or real-time data. And the objective of interTwin was to develop an interdisciplinary digital twin engine, which is defined as the software infrastructure that manages and supports the creation, deployment, and operation of digital twins. Since we're talking about digital twin applications in this webinar, in the bottom right side of this slide, you can see the role of the digital twin applications in the interTwin projects. So starting from the top, they have been providing requirements for the design and specification of the different software components. They participated in defining the blueprint architecture, and they participated also with their software releases. They integrated with the core and infrastructure modules. You will understand in the next slide what I'm talking about. And of course, they validated the different components of the digital twin engine. The high-level architecture of the project is seen in this slide. Starting from the top, since we're talking about the DT applications, you can see DT applications from, it's not shown in this slide, but from different scientific domains, broadly speaking, physics and environment, but subdomains in these broader domains, providing requirements to the different part of the digital twin engine, which is depicted in the bigger orange box. Starting from the bottom, we have the DTE infrastructure with the hardware components, HTC, HPC, cloud, and data repositories, building on top of the software, AAI, orchestrator, the federated compute, and the data management. And then we have the DTE core modules that you can see in the green boxes, and on top of that, the thematic modules that were developed by the research communities themselves to satisfy their specific needs. Moving on to the DT applications themselves. So here is the overview of the physics DT applications. I'm not gonna go into detail, but I wanted to use this slide to add the YouTube link where you can watch the webinar from last week. And I would like to focus more on the environment. These applications, which are 6 in the number. As you can see, on the top of the pictures anyway, you can see the participating partners in each use case, and then you can see some short description. I would like to be aware of the time, so I will not go through all of them. Actually, I'm not going to go through any of them at the moment, because all of them you're going to hear about in a second from our colleagues. And I would just like to use this last slide as an overview for the environmental thematic modules that were developed by our partners, to say that 19 thematic modules were developed for the environmental DT applications, and they have been covering a range of applications from machine learning-based climate extreme event analysis to hydrological flood monitoring, data integration, and decision support. The modules include components for processing Earth observation data, running scalable workflows, generating metadata, and downscaling climate data using AI. There are also several tools that focus on flood impact assessment and hydrological modeling. And we invite you to explore them in our website, where all of the information, documentation, source code, and so on is provided. And with that, I would like to pass the floor to our first speaker, which is Donatello Elia from CNCC, and Christian, to our first speakers, actually, and Christian Pazet. Donatello.
Okay, good afternoon, everyone. Thanks, Haris, for introduction. So this will be a joint presentation between me and Christian. In this presentation, we will cover the work that we've been doing in the interTwin project about the development of digital twin application for extreme climate events. Next slide, please. So we are focusing on extreme events since the increasing global warming is producing visible effects on such events, leading to an aggravation of these both in terms of intensity and frequency. For example, events like storm can have a huge impact on society and ecosystem. So providing some solutions for analysis of extreme events is quite important. Nowadays, we have large amounts of heterogeneous data, like from observation and simulation. So we can feed this information to some machine learning models that can be trained to learn the patterns associated with such extreme events from past data. And then this model can be applied on current and future climate data. So this can represent an interesting solution to traditional methods. Of course, such application based on data-driven models also carry some challenges. First of all, the whole workflow for training a new model goes like from data gathering and the preparation to the training of the machine learning model, the hyperparameter optimization. All this process can be quite time consuming and also error prone. So there's a need to simplify this workflow. Another important aspect is the fact that training such models require access to HPC infrastructures. And but also like the access like to additional system. For example, the inference could be executed on a different infrastructure than the training part. So ensuring the portability of the software ecosystem is also an important aspect. And then as a third point, as I mentioned, as this workflow is quite complex, having a solution that can track the model, the development stage is important to show the provenance of the results, but also to support the documentation and replicability of the process. Next slide, please. So in the context of the interTwin, we are developing digital twin application based on data-driven model for supporting the analysis of extreme events on climate data. In particular, we are focusing on 3 applications, which is the one about wildfire prediction, tropical cyclone detection and tracking, and the third one about extreme rainfall, temperature, and wind events change, which will be presented later by Christian. So to this end, the interTwin digital twin engine is providing the software and computer framework for simplifying the development of such digital twin workflows. In terms of user that we are targeting, we are looking to 2 different scenarios. So from one side, we have the digital twin developer, which is a more technical user that can train and validate and register a new machine learning model for the digital twin application. And from the other side, we have the digital twin user, which will actually run the trained model, selecting the input data and other arguments for like the analysis of extreme weather events. Next slide, please. So the first digital twin, which aims to locate and track tropical cyclones, we're using a data-driven approach. In particular, we're focusing on the North Pacific domain, as this is the one with the highest number of cyclones historically. We're using the ERA5 reanalysis data and EB-TRACS record, which provide the record of the historical tropical cyclone for training the model, while CMIP6 data, climate projection data for the execution of the digital twin. To support the application, a specific thematic module has been implemented. So this is the multi-seed detection is actually a library which provides the key capabilities for implementing the different pipelines. So in particular, I support multiple types of machine learning models. So we currently have two main implementations, which is one based on convolutional neural network implemented by SimCC, and another one based on graph convolutional neural network implemented by University of Trento. It also provides the pipelines for pre and post-processing the data, as well for visualizing the results. And it provides also the capabilities for running a distributed training over multiple GPUs, as well as supporting also the execution of an ensemble of machine learning models. Next slide, please. In this slide, we can see in the upper part, the algorithm which is being used by the tropical cyclone application. We already described this in a first publication from a couple of years ago, but in the meantime, the algorithm has been improved. So this is a two-step algorithm. In the first part, one or multiple models can be used to detect and locate the tropical cyclone centers. And then after we have the list of different centers, this will be linked together through a specific tracker, which can be implemented according to a set of criteria. For example, by linking tracks, by linking the tropical cyclone, which are let's say based on a certain distance. So to this end, we have implemented some script and notebooks for running the digital twin. So we have notebooks for validating the training model, as well as notebook that can be used for running the pre-trained model by selecting the climate model, as well as the time range that we want to process. And then there's the results can be visualized in some plots, as shown in the lower part of the slide, where we can see there are some of the tracks which are detected by the data-driven model, and they match more or less the ground truth, which is in blue. Of course, there are some slight overestimation, but in principle it follows, let's say, the main ones. Next slide, please. The second digital application aims to predict the extent of Barnett area at a global scale. In this case, we are using the C-sphere-cube observation data for the training of the model. This also includes some weather forecast data, and also in this case we implemented a thematic module, which is the ML4Files module, which supports the implementation of the digital twin, providing the pipelines for training the model, providing like a way to configure the setup of the model through a simple TOML file, as well as the pipelines for preparing the data and showing the results in plots and maps. Next slide, please. And here we can see some of the results of the wildfire digital twin. So also in this case, we rely on notebooks for the user interaction. So we have notebooks for validating the machine learning model with respect to the real Barnett area, but also for running the model on CMIP6 data. We can see on the right part of the slide some blocks from the notebook. So user can select, for example, the climate scenario, but also the type of aggregation they want to run, and they will get then the final map, which is shown in the lower right part. Next slide, please. So here we can see a bit what's the workflow that the digital twin developer will follow. This is, as mentioned, a more technical user that, for example, wants to train or publish a new machine learning model. So this workflow applies more or less to both the application, although here we are the snapshot in the slide refer to the tropical cyclone one. The diagram in the central part of the slide shows a bit the different components from the digital twin engine that we're using. I'll just try to highlight some of the key ones. So the developer can define a new machine learning model through a configuration file, and this is provided by the MLTC detection thematic module. And then this can be executed on a HPC system, thanks to the offloading of a Docker container, which in this case is actually a Singularity one, by using a component from the project, which is the interlink. As the training process runs, we are exploiting some capabilities from iTwin AI for like tracking the model metrics, but also for generating provenance, which is done through the YPro for ML module. And at the end of the process, the model can be re-registered on the model registry, which is based on ML flow. So thanks to the interTwin digital twin engine, we can support the whole training process in a easier and more reproducible way. Next slide, please. Then the second step is the one from the scientists that can select one of the pre-trained machine learning models for digital twin. This can be selected, for example, from MLflow, which stores all the artifacts from the model, including also, for example, the provenance document, which has been generated by YPro for ML. We can see a piece of this in the upper right part, and once downloaded, this can be done through a Jupyter notebook. We can use the thematic module capabilities, running the different parts of the pipeline, which consist of pre-processing the data, running the model, and then post-processing the output. And we can see a snapshot from this notebook in the lower part, with also a view of a map, which shows some of the tropical cyclone tracks. Also, in this case, this can be offloaded to a computing infrastructure by using the same container that we use for the training process. And part of the preprocessing are executed through a workflow component from being part of the digital twin engine, which is by Ophidia. And next slide. Okay, so I think this was management, so I leave the stage to Christian for the final digital twin for this block.
Thank you very much, Donatello, and for this section, and also Charis for the introduction. So I present you this extreme event detection digital twin. This digital twin goal is to detect and characterize generic extreme events using a novel technique, using a deep learning technique. And the data we have been using is the SEMIP6 scenario climate projection. So it's the same as it has been presented by Donatello for the wildfires, for example. And this is used both for the ML model training and digital twin execution. There's one thematic module that has been developed to support this application. It's called XTClim. Currently, this thematic module is optimized for heat waves, so it uses the surface 2 meter maximum temperature. But since the deep learning technique is generic, it's a convolutional variational autoencoder, and this is the deep learning method that is used in general to detect anomalies. And in this case, the anomalies are the climate extremes. So we can use this method to identify the different extremes on different atmospheric variables. The use of the iTwin AI that has been presented earlier by Donatello is enabling the development of this kind of application very fast, in fact, for the developer, because it offers a flexible configuration file in YAML format for users and developers. This same file is used as well to define the workflow, so the pipelines, for data pre and post processing, and also to process the data for visualization. And this workflow is implemented in the Jupyter Notebook. In this Jupyter Notebook, we have user documentation on how to configure and run and train the model, and also a tutorial on how to post-process the data to visualize the results. In the current notebook that is provided, we provide as well a sample dataset based on the CMCC SM2 climate coupled model. And but since this method can be used on any kind of climate simulations, it can be used as well with other climate models and also at different resolution. Next slide, please. So the notebooks are used for running the DTE application. So in those notebooks, the user can configure the application on the training, specifying data sets, and also doing the inference step, which is the data analysis itself. The pre-processing of data is also in this notebook to show users on how to pre-process the data properly for the model. Also, it is useful for the developers because the developers can develop different types of notebooks to show different applications of this digital twin. Right now, the training and running are done on CMIP6 projection data, and within the notebook, it is shown how to select climate model, how to select scenario, specify the time range, and also the greenhouse gas scenarios. Next slide, please. This is the main workflow of this digital twin. It is both for developers and users, as I have been explaining. So the developer, which is shown on the upper left corner, will be configuring the notebook so that it can train on the specific data sets that are expected, for example, here CMIP6. And the developer will tune this configuration so that the results are what is expected with the method. Since it is a quite novel method because this kind of deep learning method was never used to do data analysis for climatic streams, this method had to be evaluated and for its robustness in the data analysis. The user is on the lower left, has a slightly different workflow because it will use the pre-done configuration by the developer to train the specific selection of data sets that the user wants to analyze. And this will use input data from the CMIP6 that is stored on Reusio data lake. And the computing is offloaded also on the HPC computers in order to generate the results. And once the results are done in the notebook, there are some steps to create meaningful products. Like on the lower right corner, we have here the results for the summer, for the maximum temperature. And this is the frequency of occurrence of extreme maximum temperature and for different greenhouse gas scenario for one climate model. So it shows that the time increased toward the right, and we see with the climate change and also given the greenhouse gas scenario, we see an increase of the frequency of those extreme events. Next slide, please. So in summary, for this whole section, machine learning models, they are really promising alternatives to traditional approaches because it can give really greater performance, and also it is much better with large data volumes. It's those thematic modules are highly configurable, and they are easy to set up and train using this framework. Document images are provided so that all the dependencies are pre-installed, and also it enables easy portability among different systems. Integrated computing and software infrastructures are needed to automate and track the development and development step of a machine learning model for extreme events, because the easy access and the easy offload to HPC computer is very important, and the framework provided by interTwin unlock this possibility to offload the large computing to different kind of infrastructures. And this interTwin DTE, it provides really a simplified framework to support the developers of those digital twin applications. Next slide. So I don't know if we go to questions now or we wait until the end.
Yes, so thank you very much both for presenting us your work. We would have a couple of minutes for questions. I don't see anything in the chat, but if there is any question from the audience, please put it in the chat. I don't see anything. Okay, in that case, we would continue, but if there are any questions, please add them and we will come back to them later in the next Q&A session. All right, so thank you very much both. We're moving on to Willem from Deltares.
Yes. Hi. Okay, thanks for the introduction. So I'm Willem from Deltares, and I'm going to be speaking on behalf of the team from Deltares and from TU Vienna about the thematic modules that we've been developing in the interTwin project, which all revolve around flooding in some sense. Next slide, please. So flooding is one of the major hazards, obviously, that people face in inhabited areas, especially along coastlines or in estuaries. And a lot of effort is going into properly understanding these type of extreme events. What drives them? How far will the water extend? What are the impacts on communities, and how will this change in light of climate change? And in this respect, digital twins can play a significant role by accurately trying to model these compound events and the impacts that they have on the communities, and by delivering that information to relevant parties. The struggle here is that setting up these type of systems is a pretty complex thing. These type of systems are involve a lot of different moving bits and pieces, and they are being applied to very diverse regions, which each come with their own little specialities, which requires fine-tuning of the type of system. So this whole process is pretty time-consuming. As an example, an expert developer of these type of systems can spend a lot of time on a data pre-processing, gathering all the relevant data for the area of interest and collating everything together. Think hard about the model schematization. So how exactly are we going to model the flow of water through the system and what's needed for that? There's a whole deployment side of things. Where are we going to run all of these numerical models? Where's the data coming from? Where are we going to store everything? And then there's calibration and validation of the results. And this all needs to happen before any meaningful insights are derived from the system. But this is obviously a very complicated setup. Next slide, please. So what we had as a goal within this project is to set up various models to alleviate this burden of this whole process. We want to design and build integrated models that support the building of digital twins and configuring of what-if scenarios to simulate and support post-flood assessment and future planning. Next slide, please. So how does this look like? Well, this workflow is, again, like the previous case, is split into two parts, one for the digital twin developers and one for the digital twin users. So a digital twin developer comes along and wants to model a certain area. The core thematic module that does the most of the heavy lifting in this case will be Sphinx. This is a numerical physics-based process or physics-based model that will calculate the movement of water through a given area of interest. And we offer various thematic modules to interact with this numerical model, such as HydroMT and FloodAdapt, which are Python-based modules that make it easy to work with. The digital twin developer uses a notebook interface that we provide to kind of set up and configure this physics-based flood model. In the ideal case, the only thing that a developer would need to provide is an area of interest. Just drop a pin on the map and out comes a sensible model. This is, of course, not really how it works. Setting up these models is usually an iterative process. You have to go through multiple versions and check whether the outputs and inputs are sensible. Next slide, please. To aid in this whole iterative process, we also developed a thematic module which is called the Task Flood Mapper, which tries to derive water extents based on Sentinel-1 or satellite images. Whenever Sentinel-1 passes over a given area of interest and there happens to be a flood, they can capture this. And we hope that this additional information on flood extent can kind of guide the process of setting up these models. Next slide, please. How this kind of works under the hood is that this flood mapper uses Sentinel-1 data, in particular the backscatter channel, to determine whether a given area is either land or water. And then through some Bayesian modeling, we'll derive a flood probability of a given area. And in this module, remote computation is built into the system, so we can use the EODC tooling to process all the data close to where the data is being hosted rather than system. And this way we can fairly quickly get out any sensible results for satellite-derived flood maps. Next slide, please. So the developers of Digital Twin will go through this iterative process with the flood map from satellite in hand to kind of design a sensible model. And once they're happy, they can hand this system over to the end user, the DTE user or the scientist. And they, again, will be using a Jupyter Notebook as an interface, in this case, to kind of define the type of scenario that they want to run. What is the weather event they're interested in? Are there any additional features of the area of interest that they want to be included in this particular scenario versus not? And again, we provide thematic modules, HydroMT and FloodAdapt to kind of interact with the numerical model. All the data that are used to kind of update this model for a particular event is stored on a data lake. Here, think about meteorological data and water levels on the ocean side of things. Currently, we host sample data sets for our pilot use cases, but for this whole system to be globally applicable, the full scope of these global data sets will also have to be available in the data lake. Next slide, please. Once the user is happy with the scenario they defined, they can call a run function on this whole system, and in the back, a complicated workflow will trigger that will gather all the relevant data, update the model, and run the whole thing. For the compute-intensive steps, such as running this numerical model, we use another core component from Digital Twin engine to ship this off to either Kubernetes clusters or HPC clusters based on either what's necessary or what the user defined, a module called Oscar. And what this will do is that for a specific execution step, it will gather all the relevant data, move this to a cloud storage, and from there it will either be triggered. The service will either be triggered either as a Kubernetes service on there or shipped off to the HPC cluster, and then automatically be fetched back. Next slide. Once all the results are in, we also provide some extra tooling to the user to kind of evaluate, visualize what's going on, so they can get a sense of what's happening. And we have a pilot use case that can demonstrate this. If you go to the next slide, please. We have a use case along the northern coast of Germany, along the Baltic Sea, which a couple of years ago was hit by a storm, which caused some severe flooding. And here you see a map of the areas that were flooded based on the judgments of the various tools that we've been using. In orange, you see the areas that our numerical model will predict to be flooded, but only the numerical model. In light blue, the areas that only the satellite-derived product would say would be flooded, and in purple, both. And we kind of want to understand what's going on in the system and where the differences are going. Next slide. Next slide. If you zoom into a particular area, you will notice that there are spots which are kind of a bit away from the shore where the satellite-derived product does see flooding happening, but our physics-based process model does not see anything happening here. And we kind of want to figure out what's going on. Why are we missing these type of spots in our physics-based model? And can we use this information to guide how we set up this model and how we set up the particular scenario that we're running? Next slide, please. We know that this is a post-flood analysis type situation, so we kind of have a rough idea what's going on. And we know that during this storm, several dikes were breached in the area, and in other places, dikes were overtopped, so water flowing over the top of the dikes into the backlands. And this is information that we can use to fine-tune our model. Next slide, please. So we can kind of tweak a little bit with where the dikes are being breached or where dikes might have been overtopped, how many of these types of locations are there, and kind of see what happens. And we can use this to fine-tune our model. And indeed, when we do so, there seems to be a little bit better agreement between our physics-based model and the satellite-derived product, with more areas in purple showing up. Now, of course, there are still some discrepancies between the two different methods, and this can be for a host of reasons. It can be due to the timing of the satellite overpass relative to the event that we're simulating. It can be about the data quality that we use to set up the physics-based model. It can be the sensitivity of satellite products close to coastal areas, et cetera, et cetera. So there's definitely still some expert judgment involved from both the developers and the user to kind of get the most out of this type of system. Next slide, please. We can expand on the system that we've been building so far, which was only focused on post-flood analysis, to also have a more future-looking outlook into the planning of the urban planning of the area and the adaptation to climate change. The whole process looks very similar, again, being split up into a DTE, a digital twin developer, and a end user. Next slide, please. But the big difference here is the number of models that are involved. To do this type of planning work, we need to include more modules and more models. Of particular importance here is the hydrological model WFlow. This will calculate river discharges of a given area, which might be feeding into the particular area that's prone to flooding. This is particularly important for places like estuaries, where rivers and ocean boundaries come together and form a complicated dynamic behavior. Then we also need to do some impact assessments, and for that we also have two modules or tools that we've been developing. There's DelFiat, which will calculate the damage to buildings based on water levels. And there's a tool called RACE, which will assess the impact on infrastructure networks due to floods. And in this case, that will be the road network. So the overall loop for the end user is again very similar. They're provided with a Jupyter notebook that they can use to set up the different type of scenarios that they want to run. And for these type of scenario descriptions, our module FloodAdapt does a lot of the heavy lifting with defining exactly how these scenarios look like, what type of measures can be included. So you can think about storm walls or flood-proofing buildings, or assessing what's going on if a city expands in a certain area, and translate all of these type of different configurations to the specific needs of each individual model. And again, all the heavy computational burden is being offloaded using Oscar to HPCs. And we provide visualization tools to look at the outcome. Next slide, please. And so, and to get a sense what these outcomes will look like, this is kind of an interactive plot of our flood model Sphinx, with on the top all the necessary input data. You see the topography of the terrain, you can see where all the rivers are located, and the user can kind of zoom in out and click through the different types of points to see where exactly the water is flowing into the system. In orange points along the rivers, or on the coastal sides, the blue points where tidal signal is coming in. And the same information can also be overlaid on the outcome of the flood model, which is the flood map below, where the blue areas indicate the flood areas. And this way, a user can get a sense of which parts of the model are most vulnerable to flooding, which contribute most to this event. Next slide, please. Similar on the impact side of things, we have DelFiat, and we again provide a interactive map to kind of explore the scenario. DelFiat will calculate the damages to building on an individual building level, but for the ease of our own eyes, we aggregate these into, in this case, municipal boundary levels. So on a municipal level, we kind of see what the impact is on per city, but these aggregation boundaries can be whatever the user specified them to be. Not only can DelFiat do the damage to building, but they can also provide information on social vulnerability of groups of the community being hit, if such information is being provided by the developer of the system. Next slide, please. And very similar for our RACE tool, we overlay the flood map on top of the road network in the area of question and see which parts of the roads are being disrupted and are no longer usable by traffic. Not only does this provide a rich damage number, but more importantly, this will also allow us to calculate disruptions to routes So we can compare this, the optimal route from sources and destinations to the new situation with flood happening. So for instance, we can assess, can people still get to hospitals? How much longer do they need to reach certain destinations? Are neighborhoods completely cut off? Next slide, please. So to summarize, in this project, we've been building thematic and core modules that will support expert users in setting up and configuring digital twins for flood analysis and future planning. One of these modules is an Earth observation-based flood mapper, which can enhance the calibration and validation of the more physics-based process models that we typically use to model floods. The core modules and thematic modules allow faster and easier setup of these type of systems and allow for quantitative what-if scenarios and make these type of analysis more accessible to decision makers, which in the end are the ones that are responsible for climate adaptation, the disaster preparedness of the area in question, and the infrastructure planning. And with that, I'd like to thank you. Next slide, please.
Thank you very much, Willem, for presenting your work as well. We would have again a couple of minutes in case there are any questions. I don't see anything in the chat. But call to the audience if you want to ask something. Now is the moment. And I don't see something coming in. Also, being aware of the time, we might as well move to the last presentation. And if something comes up, we will catch it in the chat. Thank you very much, Willem. And Jacopo, we continue with you.
Thank you. Yes, so I'm going to present the digital twin for drought early warnings in the Alps. I'm a provider from Europe Research. And yeah, next slide. So yeah, the Alpine region is facing increasing pressure on water resources due to climate change and change in increasing temperature and change in spatial temporal pattern of precipitation. And drought early warning systems are more and more in need to improve the preparedness and drought risk management. One of the key components of this early warning system is drought forecasting. And in particular, seasonal forecasts are very interesting to drought management because of the lead time range, which is up to 7 months. And then you can water management have time to implement the preparatory action to face drought risk. However, seasonal forecast systems are very complex, and there are a mix of workflow of data, different processing and models, and as well, climate seasonal forecasts are only available, of course, with a solution, and they're characterized by high uncertainty. Therefore, the adoption of the seasonal forecast in the water sector and decision making is currently very low. And so the objective of this digital twin was to develop a high resolution hydrological seasonal forecast that integrates heterogeneous data sources in a complete and transparent modeling workflow to provide an estimate and providing an estimation of output uncertainty. That's the main goal. Next slide. So the DTE users that we're targeting are local and regional authorities that deals with water management, civil protection, and scientists that are working with so investigating the dynamic of droughts and especially droughts. And the functionalities that we developed during this interTwin project a web editor that can manage and run the overall workflow, so this complex workflow to predict seasonal hydrological seasonal forecast, and then the possibility to use different data inputs from cloud-based catalog, and I will explain in the next slide what is that catalog. Then the possibility to customize and configure the hydrological model to to the preferred resolution. In this DTE, we have developed hydrological model we configure the hydrological model that runs a 500-meter resolution in daily, and then the possibility to calibrate this model with satellite information and to increase the resolution of this seasonal forecast by downscaling it. The domain of the DTE is showed in the top right figure. It's on the Alpine, most of the Alpine region, and then on the bottom right you can see the scheme of the modeling solution in pipeline. So essentially, we use we calibrate a physical-based model, which is the WFlow SPM that was presented in the previous presentation by Willem. It's a delta-test model. And so the first step of this modeling pipeline will be to emulate using a deep learning model, and then that kind of learn to produce a robust distribution in surface and moisture. These are the two key target variables that we are tackling with this DT. And then for the emulator, we can use the emulator to calibrate this WFlow SPM model using satellite estimates of surface and moisture. And then the calibrated parameters can be used together with the seasonal climate forecast from SNWF to then produce the hydrological forecast of the transpiration and surface and moisture for the next 7 months at the daily resolution. Next slide. This is an overview of the overall DT module integration diagram. There are two workflows for the two users. The TTE developer are the user that is essentially configuring the model, training the model, and that then it will be available for the actual DT users, which are, let's say, scientists for the technician, civil protection, and so on. And I will then explain in more detail in the next slide the different thematic modules and core modules that support this digital twin. Next slide. So I will start with the data catalog and processing. As you see on the top right, it sits in between the two user workflow, because as I said, the developer will produce data and will read data, and then this data can also be used by the other user, and the data are published in the stat catalog, which is special temporal asset catalog, which is a catalog that organizes and describes geospatial data and observation data. And all the data that we are using in this DT are published in Stack, on the Stack instance of the interTwin infrastructure. There is a link at the bottom of the slide. And the possibility to read and publish Stack collection, called the dataset, is possible thanks to the thematic module, which is also to Stack. It's available on GitHub, it's a Python package, and then the overall data processing, efficient data processing of data, it's possible thanks to the two modules developed within the interTwin project, which are the OpenEO gparser and OpenEO processes that leverage task computation. The DT is using a diverse and heterogeneous list of dataset from climate variables to hydrography, soil properties, and referring the spatial elevation model across climate seasonal forecast. Next slide. So this is the workflow of the DT developer. The DT developer the interface. The DT developer is the web editor of the of OpenEO. OpenEO is a open source standard, API standard, that simplify the access, processing, and analysis of Earth observation data from different events. And so during interface, we have implemented a new process in a new OpenEO process, which is called Run Oscar, that interact with the Oscar API. And the Oscar API, Oscar is a service of interTwin. Of the DT that can execute container in cloud environment. So each of the, let's say, black boxes that you see in the workflow can be run is containerized and can be executed for an OpenIO that can execute faster. The two first black boxes is the I20 and Tableau are the model builder and model runner. So so these two components are used to build the physical-based operational model. And then I20 AI is the AI framework developed in interTwin. It's a core service that is support AI pipeline and training on HPC. And it has been integrated with the Python WSDN emulator, which is this surrogate emulator that we use to train the emulator and perform the calibration of the model. So far, it's possible to run each individual component, but it's not yet possible to connect the different components in a chain OpenIO process graph. Next slide. This slide shows the tools that are available for the DTE developer, digital twin user developer. Thanks to the I20 module, for example, the model registry, it allows the store let's say model that has been trained and also to perform experiments, and then array, which can be used to run hyperparameter optimization, which is very useful for optimize deep learning emulator. As well, the whiteboard, it's a service, no, it's a module to essentially track and log the workflow, the AI workflow. And then finally, WSDN, the emulator, has this uncertainty quantification approaches realistic pair, which is Monte Carlo, conformal prediction, and probabilistic output, and then can be used as an indicator of the quality of the model, which is an important indicator for the digital twin user. Next slide. So that's we are describing the digital twin user workflow. So again, the interface is the OpenIO web editor, and an additional module that we use in this that the user can use is the downscale ML, which is essential to improve the resolution of the course seasonal forecast. This you can see an example of the OpenIO processes that are chained together to then run the downscale ML seasonal forecast. The I20 AI is still used to load the machine learning, the deep learning emulator, and the calibrated parameters that are stored in the ML flow model registry, and calibrated parameters are stored as artifacts. And then to I20 AI can also be used to produce images that at the moment are simple PNG files that stored in there. So that the visualization has been yet developed in this data within the OpenIO, let's say, user interface. Final, next slide. Yeah. So in summary, we show that the OpenIO industrial integration can be used to run complex workflow. Access to stock Thematic module can enable the access to different cloud-based general data inputs. Then the use of I20 AI and WSDN emulator was important for calibrating and exploiting satellite data, distributed satellite information. As well, the emulator was useful for improving the computational efficiency and therefore to estimate the uncertainty of the model. And finally, the downscaling increased the resolution of seasonal forecast. So this leads to the fact that with this type of DTE, the DTE user can run complex workflow and have the stability of data and processes. They can use hydrological seasonal forecast that address the local user need impacts, and then also they can have access to the uncertainty of this of the available workflow and model output that can be used to support decision making. It is a stop.
Thanks a lot, Jacopo. Right on time, it's 3 o'clock. We don't have time, but if there's any burning question from the audience, I guess we could make a minute or two. If there is anything, please drop it in the chat, the Q&A box. And in the meantime, I would like to mention again that in the interTwin website, you can find an elaborate description of all of these use cases, along with the physics use cases, their implementation steps, the description of the thematic modules used, their documentation, their code, everything that you need, basically. So be sure to visit it. And since I don't see any question and we are late already, I would say let's close this webinar here. Thank you very much for participating. Thank you very much to the presenters for presenting your work over the last 3 years. And we will keep in touch, I guess, through our interTwin channels, media channels. Thank you very much.
Thank you.